Transformer core grounding is a critical aspect of transformer design and operation. While it may seem counterintuitive to ground a core that is otherwise insulated from the tank, this deliberate grounding serves a vital purpose in preventing damage and ensuring safety. The primary reason for core grounding is to mitigate the risks associated with inadvertent grounding. An inadvertent ground on the transformer core can create a circulating current path between the core and the grounded tank. This circulating current can lead to several detrimental effects, including eddy currents in the core, arcing between core laminations, and magnetic imbalances. Eddy currents are circulating currents induced within the core material itself due to the changing magnetic field. These eddy currents generate heat, which can lead to overheating and damage to the core insulation. Arcing between core laminations can occur if the insulation between the laminations breaks down, creating a short circuit. This arcing can further damage the core and potentially lead to transformer failure. Magnetic imbalances can affect the transformer's performance, leading to reduced efficiency and increased losses. To prevent these issues, a dedicated grounding strap is connected between the core and the tank. This grounding strap provides a controlled and intentional path for any circulating current to flow. By providing a low impedance path to ground, the grounding strap effectively prevents current from flowing through the core itself, thus mitigating the risks associated with inadvertent grounding. The grounding strap is typically made of copper, which is a good conductor of electricity. The size of the grounding strap is determined based on the transformer's rating and the potential fault currents that it may need to handle. It is crucial to select a grounding strap that is adequately sized to ensure that it can safely carry the fault current without overheating or failing. It is important to understand that core grounding is not intended to protect against phase-to-ground faults. Phase-to-ground faults are typically handled by other protective devices, such as circuit breakers or fuses. Core grounding specifically addresses the risks associated with inadvertent grounding on the core itself. The grounding strap should be properly installed and maintained to ensure its effectiveness. The connection between the grounding strap and the core, and between the grounding strap and the tank, should be clean and tight to provide a low resistance path to ground. The grounding strap should also be inspected regularly for any signs of damage or corrosion. Firstly, ensure the core insulation is intact during installation or maintenance. Secondly, verify that the grounding strap is properly connected to both the core and the tank. Thirdly, routinely inspect the grounding strap for damage or corrosion. Ignoring these steps can compromise the effectiveness of the core grounding system. Core grounding is a critical safety measure that protects the transformer core from damage due to inadvertent grounding. The grounding strap provides a controlled path for circulating currents, preventing them from flowing through the core and causing overheating, arcing, or magnetic imbalances. Proper installation and maintenance of the grounding strap are essential to ensure its effectiveness. Consider the NEC, National Electrical Code, Section 450.10, which addresses grounding of transformers. While this section primarily focuses on grounding the transformer enclosure and associated equipment, it indirectly reinforces the importance of proper grounding practices within the transformer, including core grounding. Although the NEC doesn't explicitly detail core grounding procedures, adherence to its general grounding requirements contributes to overall transformer safety. Proper core grounding helps maintain the integrity of the transformer's insulation system, reducing the risk of ground faults and subsequent electrical hazards. Core grounding prevents the buildup of static electricity on the core. Static electricity can discharge through the core insulation, potentially damaging it over time. The grounding strap provides a path for static charges to dissipate safely to ground, preventing insulation breakdown. Core grounding minimizes the risk of touch potential hazards. If the core becomes inadvertently grounded and a person touches the transformer tank, they could be exposed to a dangerous voltage. The grounding strap ensures that the tank remains a ground potential, reducing the risk of electric shock. Core grounding improves the reliability of the transformer by preventing core damage that could lead to premature failure. A damaged core can cause increased losses, reduced efficiency, and ultimately transformer downtime. By protecting the core from damage, core grounding extends the transformer's lifespan and reduces maintenance costs. The absence of a core ground can lead to localized heating within the core, which can accelerate the aging of the insulating materials. This premature aging can result in reduced dielectric strength and increased susceptibility to insulation failure. Grounding the core equalizes the potential, thereby reducing the stress on the insulation. The core ground provides a reference point, preventing voltage differences between the core and other grounded components. This minimizes the electrical stress on the insulation, extending its life and improving the transformer's overall reliability. Core grounding aids in reducing electromagnetic interference, also known as EMI. Inadvertent core grounds can cause circulating currents that generate electromagnetic fields. These fields can interfere with nearby electronic equipment, causing malfunctions or inaccurate readings. The grounding strap minimizes these circulating currents, reducing EMI and ensuring the proper operation of sensitive electronic devices. In some cases, a core ground fault can cause nuisance tripping of protective devices. If the circulating current due to an inadvertent ground is high enough, it can trigger ground fault relays or circuit breakers, interrupting power supply. This nuisance tripping can disrupt operations and cause unnecessary downtime. The grounding strap prevents these circulating currents from reaching levels that would trigger protective devices, improving the stability of the power system. Core grounding, while seemingly a small detail, is a fundamental aspect of transformer design and maintenance. It's a proactive measure that safeguards the transformer against unforeseen issues, ensuring its safe, reliable, and long-lasting operation. In distribution transformers, core grounding is just as vital as in larger power transformers, though the scale and methods might differ slightly. These transformers are closer to end users, making safety and reliability even more critical. Distribution transformers frequently serve sensitive loads, such as residential areas, hospitals, and small businesses. An inadvertent core ground in these transformers could disrupt power to these critical facilities, causing inconvenience, financial losses, or even safety hazards. Therefore, proper core grounding is crucial to ensure a stable and reliable power supply to these sensitive loads. The grounding strap used in distribution transformers might be smaller in size compared to those used in larger power transformers, but its function remains the same. It provides a low impedance path for circulating currents, preventing them from flowing through the core and causing damage. Regular inspection and maintenance of the grounding strap are essential to ensure its effectiveness. In some distribution transformers, multiple grounding straps might be used to provide redundant grounding paths. This redundancy further enhances the safety and reliability of the transformer by ensuring that there is always a path for circulating currents to flow to ground, even if one of the grounding straps fails. The location of the grounding strap on the core and tank can also affect its effectiveness. The grounding strap should be connected to a point on the core that is close to the source of potential circulating currents. This minimizes the length of the current path and reduces the impedance to ground. Similarly, the grounding strap should be connected to a point on the tank that provides a good electrical connection to ground. The grounding strap connection point should be free of corrosion and other contaminants to ensure a low resistance connection. The material used for the grounding strap can also affect its performance. Copper is the most common material used for grounding straps due to its high conductivity and corrosion resistance. However, other materials, such as aluminum, can also be used in certain applications. The selection of the grounding strap material should be based on the specific requirements of the application, including the potential fault current, the environmental conditions, and the cost. The grounding strap should be installed in a way that minimizes the risk of mechanical damage. The grounding strap should be routed away from sharp edges or other objects that could damage it. The grounding strap should also be protected from corrosion by using a suitable protective coating. The grounding strap should be inspected regularly for any signs of damage or corrosion. If the grounding strap is damaged, it should be replaced immediately. The frequency of inspection should be based on the environmental conditions and the potential for damage. In corrosive environments, the grounding strap should be inspected more frequently. In addition to the grounding strap, other grounding methods can also be used to protect the transformer core from inadvertent grounding. These methods include the use of ground fault relays and the installation of a grounding electrode system. Ground fault relays are devices that detect ground faults and trip a circuit breaker to interrupt the flow of current. A grounding electrode system is a network of interconnected grounding electrodes that provides a low impedance path to ground. These additional grounding methods can provide additional protection against inadvertent grounding and enhance the overall safety and reliability of the transformer. Core grounding is a vital part of transformer maintenance. Neglecting this can lead to significant operational problems. Regular checks of the grounding strap's condition and connections can prevent issues down the road. For instance, a loose connection can increase resistance, reducing the effectiveness of the ground. Corrosion can eat away at the strap, weakening it and potentially causing it to fail under fault conditions. During maintenance, it's important to use appropriate tools and techniques. Over-tightening connections can damage the strap or the terminals. Under-tightening can lead to loose connections. Using the correct torque specifications is crucial. Also, when replacing a grounding strap, make sure to use the correct size and material. An undersized strap may not be able to handle fault currents, while a strap made of the wrong material may corrode quickly. Before working on any transformer, always de-energize it and follow proper lockout-tagout procedures. This ensures that the transformer is safe to work on and prevents accidental energization. Working on energized transformers can be extremely dangerous and can lead to serious injury or death. After completing any maintenance work, thoroughly inspect the grounding strap and its connections. Make sure that all connections are tight and that the strap is free of damage. Use a multimeter to verify the continuity of the grounding path. This ensures that the grounding strap is properly connected and that it provides a low impedance path to ground. In addition to visual inspections, consider performing insulation resistance tests on the core. This test can help identify any insulation damage that could lead to an inadvertent ground. A low insulation resistance reading indicates that the insulation is compromised and that the core may be susceptible to grounding. In such cases, the transformer should be taken out of service and repaired. Understanding the principles behind core grounding is essential for anyone working with transformers. It's not just about following procedures, but also about understanding why those procedures are in place. This knowledge can help you identify potential problems and take corrective action before they lead to serious issues. For example, if you notice that a transformer is running hotter than usual, it could be a sign of an inadvertent core ground. By understanding the principles of core grounding, you can quickly diagnose the problem and take steps to correct it. Core grounding is a critical safety measure that protects the transformer core from damage due to inadvertent grounding. The grounding strap provides a controlled path for circulating currents, preventing them from flowing through the core and causing overheating, arcing, or magnetic imbalances. Proper installation and maintenance of the grounding strap are essential to ensure its effectiveness. Ignoring core grounding principles can lead to transformer failure, safety hazards, and costly downtime. Therefore, it's essential to take core grounding seriously and to follow proper procedures for installation, maintenance, and testing.